Okay, let's get started. So welcome everyone to the second virtual QSI seminar. Today it's a pleasure to have Chris Jackson from CQuick and a future unspecified, uncertain start date at QSI, provided he can travel at some point in the future. So Chris will be telling us about fermionic phase spaces and coherent states and measurements. Take it away, Chris.
Oh boy. All right. Good afternoon, everybody, and good morning. I'm currently on the West Coast in the US, and I'm very happy to be here. Thank you for coming. So yeah, as Chris was saying, I'm going to be talking to you guys about fermion measurement. So I think a little about myself first. So I am becoming, or my expertise is in differential geometry at this point. So I feel a good place to get started is to give you guys a brief history of how differential geometry came to be. Okay, so the 19th century was a fantastic century as far as differential geometry was concerned, initiated by first the discovery of non-Euclidean geometries. Okay. And it wasn't until about 25 years later that Riemann came into the picture and pointed out that these non-Euclidean geometries were non-Euclidean because they had curvature. So what does non-Euclidean mean? Well, you know, Euclid back in something like 600 BC was known for his masterpiece called The Elements. And in there, he had 5 axioms in which he derived all geometric truths. And the 5th axiom is a particular assumption on how parallel lines behave. And this guy Lobachevsky was able to construct logically different kinds of geometries which changed the assumption of this 5th axiom of Euclid. So that's what non-Euclidean means. But then Riemann was able to take that entire set of axioms and show that it's equivalent to just thinking about spaces that have curvature. So you might be familiar with that, but what you might not be familiar with is that later this whole notion of a Lie algebra was invented precisely. Well, that's not true. It turned out that this discovery of Lie algebras was a different way of thinking about the curvature of a manifold. And I would say that differential geometry reached a sort of apex in its development in this year 1926. Soon after Cartan met Hermann Weyl, in which it was shown that manifolds of constant curvature actually are only made out of sort of a fundamental set of manifolds, which belong to a family of 27. So that's fun. Okay, so why do I bother telling you guys about this? Well, what's cute is that these manifolds of constant curvature have been discovered independently over and over again in physics problems. So let's go through this list a little bit just because it's fun. So maybe a bunch of you are familiar with the singular value decomposition. So it turns out that you can think of positive operators as a manifold of constant curvature. And understanding how they interact with unitaries, there's an entire geometric picture. And in fact, the perspective is the same if you think about things like pendula moving around the Earth, relativity in space-time, Hamiltonian mechanics, rotations, quantum mechanics, random matrix theory, optical squeezing, transverse Ising models, my favorite, falling cats, nuclear magnetic resonance, quantum illumination, something that was actually demonstrated by some friends of mine recently, that this is also a kind of just a different way of thinking about matrix decomposition. And the one I'm going to talk to you a bit about today, which is the relationship of these with what's called the generalized coherent state, POVM. Okay, all right. So that being said, quick review of how this talk is going to go. So what I'm first going to do is talk to you guys about spin coherent state measurements, just because spin is easier to understand because we live in 3 dimensions. I'm going to tell you about some work that I had done a couple of years ago. And then I'm going to quickly segue into how this work generalizes, and then quickly re-specialize to the case of fermion coherent state. Okay. All right, so let's get started. I think a great place to get started in terms of geometry is to think of the two simplest kinds of two-dimensional geometry, which are the plane and the sphere. And so I'm going to try to explain to you how I think of the plane and the sphere. I think the easiest way to describe their differences is by thinking about what triangles look like inside of these spaces, okay? So called trigonometry. And in which case, what do you need to define a triangle? Well, you need the notion of a straight line, and you need the notion of angles, okay? So it turns out that there's this great way of describing how angles and straight lines interact with each other in the flat plane, which is in terms of what's called the Weyl-Heisenberg group. So there are these things called displacement operators, and you can think of, well, if I move to the right, it has a generator we call P, or if I move up, it has a generator called Q, and it's the interaction of these two such that if I had two displacement operators that I composed, I get displacement operators corresponding to straight lines. I get a new straight line, but I also get this extra term corresponding to the sort of area in the middle, okay? So the same thing is true for the sphere. You think about a different kind of set of displacement operators that take you from, say, the North Pole, and you can compose them and get notions of new straight lines given two straight lines that you compose, and a wonderful term that you get off the side coming from the area subtended by the triangle. Okay, so these displacement operators, what's miraculous is that their multiplication rules are completely defined by their so-called Lie algebra. Okay, so this was me trying to just real quickly flash a bunch of math at you guys that you might be familiar with, but perhaps in a different setting. So I'm going to assume that many people in this audience have come across these kinds of commutation relations and played with them a bit in the context of certain kinds of quantum mechanical systems. You might be more familiar with this kind of commutation relation in the context of Pauli matrices, in which case there'd be a factor of 2 here. And then what I'm telling you with authority is that there is in fact an entire story of geometry behind these commutation relations. Okay? My favorite applications of these two geometries, of course, are music, because music can be thought of as time frequency localized signals. And you can think of this Q as a time and this P as a derivative with respect to time, and then this being just what they are, their commutators. And my favorite application of course, the sphere is the star, either of which are quantum. Okay. But of course, this is going to be a talk on quantum theory. So are there any questions at this point? Before we quantize these geometries, yeah, I just flashed a bunch. Are there any questions? Am I responsible for raised hands? Is this something I should be paying attention to?
Yes, I was just going to ask.
This list, Chris and I can keep track of that if you like.
Okay, so
yes,
my question was going to be, can everyone unmute themselves, or is that something the hosts have to do?
No, everyone can unmute themselves, I believe.
Okay. Okay. So I guess they can interrupt.
So they can always just unmute themselves and say, hey.
Yes.
Hey, Chris.
Great. Okay. So great. Thank you very much. So if there are no questions, then let's quantize these geometries. So what does it mean to quantize? It means that you replace a point in the manifold with instead a bump of quantum fluctuation. Right? So formally, this means the introduction of the Hilbert space and an understanding of the kind of observables you can have over that Hilbert space. So what I have down here are 4 different ways of defining so-called coherent states, which are a way of thinking about quantizing geometry. So on the left, we have, when we quantize the plane, there are a particular set of motions in the plane that are easy to solve dynamically. These are the so-called harmonic oscillators. So you should think here of omega as a constant and P and Q as variable constants. So omega is just some fundamental constant as far as the problem is concerned. It's the natural frequency of your oscillator. But then P and Q are things we're imagining to be different and varied. So for each P and Q, you have a ground state, okay? And the collection of these ground states are called the coherent states, okay? So they are in many ways the most classical kinds of states in the theory because they correspond to the most benign of problems that you could construct with these kinds of observables. Okay? Similarly, in the spherical case, we have the same notion, except now we're not talking about harmonic oscillators. We're talking about magnetic fields interacting with spin. And this is the sort of easiest set of Hamiltonians you can think of that can generate dynamics. And each of them has a ground state. Okay, so that's one way to define coherent states, is as ground states to easy problems. Okay. Another way you can think of coherent states is in terms of these displacement operators acting on a fiducial state. So what's great is that all of these observables are connected to each other by conjugation by these displacement operators. So this minus P and this minus Q, you could have actually written as just P and Q equal to 0 being conjugated by the appropriate displacement operator. So all of these points are connected to each other. Okay, so you can think, in this case, the origin is called the vacuum state, and all other coherent states are then just displacements from vacuum. Same in the sphere, this state JJ, which is the ground state of JZ. This is a standard choice that's usually made. All of the points on the sphere can be thought of as displacements from that state, which you can think of as the north pole of a sphere. All right, so that's a second definition. This is sometimes called the Paralymov definition. Paralymov being speaking to the spirit of a fiducial state, being so-called orbited by representations of a group. All right, but the most calculationally useful is...
Chris.
Oh, hello, hi.
Yeah, hi. Can I ask, I feel like I really should know the answer to this question already, but since I don't, I'll ask it anyway. So I understand with a harmonic oscillator that, you know, the vacuum state is the ground state. But you mentioned the fact that you could interpret these coherent states at a particular PQ and P and Q also as a ground state.
Right.
What is the Hamiltonian that you have to have for that to be the ground state for?
Yeah, fantastic. So thank you for that question. So what I have written here is not quite the Hamiltonian of the harmonic oscillator you'd probably think of, right? This harmonic oscillator is shifted so that its fixed point is at this place P and Q, right? So this is actually the ground state of this Hamiltonian. So I might have called this also a harmonic oscillator, and maybe I shouldn't still call this a harmonic oscillator, but I did. Does that answer your question?
Right. Okay. So basically, it literally is the ground state in a displaced phase space.
Yeah.
In some sense.
Yeah.
If you have that in the kind of the Hamiltonian picture of H bar omega A dagger A, is it like now A dagger minus something times A times something? A minus something, is that how it works?
Yes, exactly. Yeah, so this is going to be equivalent to A dagger minus alpha star times A plus alpha minus,
minus alpha.
Yeah, so instead of A dagger A, you would get displaced A dagger times displaced A.
Okay, right,
and this
great.
would be the ground state of that. Great.
Okay.
Yeah, so that in fact brings me to exactly this third item, which is you can think of them as being annihilated by the corresponding ladder operator, right? Just like you could think of this as an A dagger A, and each of these as ground states of that A dagger A plus a half. You could just as well think of them as uniquely defined by being annihilated by the corresponding lowering operator. Okay, so usually people think of this in terms of being eigenstates of A, But the reason I chose to write it like this sort of co-moving lowering operator, is because then you can write down the analog in the spherical case, which is, like JJ is uniquely defined by being annihilated by J plus, but then there's this sort of rotated J plus, which uniquely annihilates one state, which is the corresponding coherent state. All right. And then finally, we have this fourth definition of a coherent state, which makes the two actually look quite different. So something you might have noticed on the left is that there isn't sort of an extra quantum number like there is on the right, right? On the right, we have this quantum number J that we imagine as fixed, but it sort of doesn't appear on the left, the analog of that. And there's a simple reason for that, which is when you add quantum fluctuations to a sphere, well, a sphere actually has a radius. So when you introduce quantum fluctuations, they will always have a size relative to the radius of the sphere, while a plane does not have a size, right? So when you add quantum fluctuations, there aren't really different ways of quantizing the plane. And this is reflected by the following fact, which is you can consider copies of these coherent states that you started off with. And the fact is that this is unitarily equivalent to a bunch of vacuum tensored with just a rescaling of the original coherent state you started with. So this unitary would be something like its inverse would act so that it puts all of the amplitude of n modes into one mode. So for those of you who know a little optics, you might very well know what this unitary is. While in the spin coherent state case, you can still consider taking copies of a fundamental representation, in this case, the spin half representation. But what you get is actually something new, a different Hilbert space. You might also come across this on the left under the name of the Stone-von Neumann theorem, which is that there's only one way to quantize this kind of geometry. And that's essentially because the way you would construct other kinds of representations or quantizations are just the same as rescaling. Okay, so for spin, copies gives you different kinds of quantizations, while for the usual Weil-Heisenberg case, copies do not give you different quantizations. Any questions? All right. Okay, so why might you care about spin coherent states? I want to suggest to you, well, these guys, okay, that's how I should say it. So in '95, these guys were interested in spin coherent states because of the following task that they imagined. They imagined that you were given 2J copies of an unknown qubit, and what you want to do is perform whatever measurement you can, which is the best measurement for guessing correctly this unknown direction as quantified by this thing called the average fidelity of estimation. So just to parse this a little bit. So this is an integral over all possible, this is an average over all possible values n naught could take. This probability is calculated according to quantum mechanics. And this is just a quantity that is 1 when you guess perfectly correctly. So n hat of k is going to be the guess you make given the outcome k of whatever measurement you decide to do. And then this thing is just monotonically decreasing from 1 as you get worse and worse a guess between n hat of k and n hat naught. All right, so it's actually easy to calculate the bound of this over all possible measurements you could do. And this bound is saturated by the so-called spin coherent state measurement, which is the measurement whose outcomes are projectors onto the same kind of state as this unknown state has been prepared. All right, are there any questions there? Okay. So I'm about to tell you guys how to do this measurement. So just to emphasize again, even though you can mathematically optimize this problem and figure out this POVM that saturates it, it doesn't mean you actually know how to do this POVM. Okay, so I'm going to tell you guys how to do the POVM, but before I do that, I'm going to quickly review some generalized measurement theory. Okay, so what am I imagining here? So in the bottom, I have the original Hilbert space of interest in which I have some state prepared rho. And I'm going to couple it to a Gaussian meter state. Okay, so one whose wave function is given by this. Okay, so the coupling is going to be written in this way. So I'm going to anticipate quite a few things. So you should just think of this as creating a weak displacement. If you're familiar with stochastic theory, then you're going to know very well why I decided to write the small number as the square root of gamma dt. But if you're not, then you should just appreciate that this is small, but small in a very particular way. So I'm going to couple the meter state to the original Hilbert space of interest according to this Hamiltonian for the time I do, and do a measurement on the meter state after the interaction in the same basis that these Q's are eigenstates of. Okay, I'm going to call that outcome dW sigma, with dW being a Wiener increment when dt is small. All right. So what's great is that you can rewrite all of this, the effect of all of this on the original Hilbert space of interest in terms of what's called Krauss operator. So I'm going to write these Krauss operators as follows. So there is the X, which is the observable in the Hilbert space of interest that you had coupled to. Then there's the dW, which is the outcome of the meter state having been measured after weakly coupling to the Hilbert space of interest. So you write it all out and you can calculate what these Krauss operators are, and they're going to be these displaced Gaussians. So I've written this in a particular way that will become clear later, but you should see that it has the form that it does because the meter state had the wave function that it did. Okay, and maybe just to point a few things out, so dW was a Wiener increment, X is an operator associated with whatever observable is in the system of interest. Okay. All right. Now, once we have these Krauss operators, then over the set of outcomes that you could get in the meter state, you have a so-called POVM. So for every outcome dW, there is this action on rho, and the trace of this is in fact the probability that that would have happened. Oopsie. Excuse me. So the trace of this is the probability that that would have happened, and therefore the probability of any given set of dWs is given by the integral over that region. Are there any questions here? Okay, if there are no questions, then let me introduce you to the isotropic measurement. So what is the isotropic measurement? So I have a little graphic here as inspired by Chris Ferry. So what I'm imagining here, let me play it again because it's nice. Okay, what I'm imagining here is this black, you know, I don't know, what do you call this thing? This black thing with a bunch of white dots in it is supposed to represent 6 copies of an unknown qubit, okay? And what I'm doing is I'm coupling it, its spin, its collective spin, to the polarization of 3 beams of light that are orthogonal to each other with orthogonal polarizations. I believe this is what's called a Stokes interaction. And then I do a measurement on the polarization that has just weakly interacted with this spin ensemble. These are the outcomes of the function of time. And this is called an isotropic measurement because I am imagining coupling with equal strength to the X, Y, and Z components of spin in the ensemble isotropically. Okay, that is with equal strength. Okay, so this is the Krauss operator of the isotropic measurement. So at any moment dt in time, I have done effectively 3 measurements that commute with each other because these Krauss operators are weak. But then I continue to do this measurement for a finite amount of time. And then it's easy to show that, in fact, these kinds of Krauss operators with probability 1 always become of this form, which is the tensor product of a ket in a spin coherent state and a bra in a spin coherent state. So mathematically, the reason why you want to do an isotropic measurement is because these quadratic terms in the fundamental Krauss operators under an isotropic measurement don't do anything, as represented by the fact that they sum up to a so-called Casimir operator. So if you want to know more about this, I encourage you to take a look at this paper. Are there any questions here? Let me grab a time device real quick so I can make sure. Oh my God, okay. So now I'm going to tell you that this measurement generalizes. So all you need to do to generalize is define a notion of fiducial state and a notion of isotropy, and then Bob's your uncle. So in this case, the fiducial state I'm imagining orbiting are the ground states to easy problems corresponding to the generators of some Lie group. Okay. And so this D of G is then, G is an element of some Lie group, and these J's are the generators of that Lie group. And there are a bunch of lambdas that you can think of as different kinds of ground states of these kinds of generators. All right, so so this thing is called the Killing form, which is a kind of metric between generators in the group. And when this metric is invertible, then you have a Casimir operator, which means you can do all of the exact things we did on the last slide, but in the generalized case. So there's a special name for when this metric is invertible. It's called semi-simplicity. And if you're at all familiar with the theory of Lie groups, then semi-simple Lie groups enjoy a classification theorem, as is often denoted by these Dinkin diagrams. And this is the corresponding isotropic measurement. So here, oh, I'm so sorry. These X mu's are supposed to be the same thing as J mu's. The J's or the X's being a basis for the Lie algebra of the group you're representing. And just like in the spin coherent state case, these isotropic measurements have the following destiny, which is that they are always a tensor product of a generalized coherent ket with a generalized coherent bra. Okay, so this is great. And this is actually a property that is enjoyed in algebraic geometry under what's called the Borel fixed point theorem. If any of you have a mathematical background and know a bit about this, I'd love to talk to you about it further. But if you want to know more about this, I encourage you to look at this paper. All right, these are ways of depicting the same effect in SU3 coherent states. But I will leave these diagrams as mysterious for now. Okay. So as promised, looks like I only have like 10 more minutes, but we will get to the punchline, and I think you'll find it exciting. So specializing now to a particular kind of coherent state, I want to talk about fermions and these so-called Bardeen-Cooper-Schrieffer coherent states. So what are fermions? Well, fermions, of course, have quite a history in terms of their physical realization. From a mathematical point of view, fermions are very easy to describe in terms of these so-called canonical anti-commutation relations. So these C's are ladder operators similar to bosons, so they virtually create and annihilate particles. And this squiggle bracket is an anti-commutator, which is to say, if this was A and B, then this is AB plus BA. And so this is called a canonical anti-commutation relation. And you can think of them, these operators, as having a real and imaginary part. These real and imaginary parts are called Majorana operators. So I'm also tempted to call these canonical anti-commutation relations. This G mu nu, you can just think of as diagonal. That is equal to 1 when mu is equal to nu, and 0 when mu is not equal to nu. All right, who are Bardeen-Cooper and Schrieffer? Well, they were these guys who were the first to correctly predict. Hello?
Yeah. Quick random question. Why do you use G mu nu instead of delta JK? It sounds like it's the same property.
Yeah, that's a wonderful question. So when you think of this as delta mu nu, the way I think of it is you've normalized your system so that the energies of each mode are just considered to be measured on the same scale. And you've also designed your modes such that they're sort of orthogonal to each other. So I always like to write this G mu nu because it turns out that there's so much you can do without ever, just by appreciating that this is positive and symmetric. So to me, this is sort of paying homage to some really large degrees of flexibility that calculations have.
So your G mu nu, I thought you said it was 1 on the diagonal, but what you're saying is it can be a positive number on the diagonal and 0 elsewhere. Is that what you're saying?
Right, this could be any positive symmetric matrix and the whole thing still works. Yes.
Great.
Great, thank you so much for your question. All right, so BCS were the first to successfully predict superconductivity. And what they essentially did is showed that the really cold conductors satisfy this kind of a Hamiltonian. This kind of term just showing up because electrons can move around. This kind of term showing up because of the Coulomb potential experienced by the lattice vibrating. And then this being a mean field approximation. But then what's important to us is that this effective Hamiltonian of B, C, and S is quadratic and therefore can be diagonalized simply. And the kind of unitaries that diagonalize these kind of Hamiltonians are called Bogoliubov transformations. And these Bogoliubov transformations form a group called the spin group, which is essentially the same as the group SO2N up to a double cover. If you guys have ever thought about spin systems, this is the same kind of double cover that shows up. And because this is in fact a semi-simple Lie group, there is a nice sort of terse way of describing everything you could ever want to know about this group in terms of a Dinkin diagram. All right, so the BCS-coherent states, what I'm calling BCS-coherent states, and I think a lot of condensed matter people like to call them these days coherent states, are just the ground states of these BCS Hamiltonians, okay, which can be thought of as Bogoliubov transformations on a vacuum state. Any questions? All right. So just to repeat, so the slide before this was saying that you can, in fact, do measurement of the, you can do a generalized coherent state measurement for any semi-simple Lie group. So that includes this one. So you can think of these, sorry. So there's a special name for this manifold of BCS coherent states in geometry. It is the manifold D3. Okay, so you can think of these generalized coherent states as the outcomes of a POVM. Okay, and in this case, because we're only considering quadratic Hamiltonians or Bogoliubov transformations, these kinds of projectors or outcomes resolve the even parity identity. So this is half of the Fock space that you probably usually imagine. Okay. If you're at all familiar with phase-space correspondences, the outcomes of this measurement given a state rho have a special name. They're called Q functions. But that's besides the point. So here is the even parity Fock space. Its dimension is 2 to the n minus 1, where m is the number of modes. And if you were to just think of this as a naked Hilbert space, and you imagined trying to do measurements in the sense of standard tomography, so that you could uniquely determine the sort of unknown density operator being given to you, you would immediately think that doing tomographically complete measurements on such a Hilbert space might be hopeless, because the Hilbert space has a dimension that is exponential in the number of modes. And you, if you're building a quantum computer, would be interested in a system with many modes. But wonderfully, I'd like to point out that this isotropic measurement actually only requires you to measure quadratically many observables. And in fact, this measurement is still tomographically complete in the even parity sector. This is a reason why you might be interested in this kind of measurement. Okay, so just to reiterate, the kind of observables you're measuring isotropically are these quadratic observables in the fermion operators. Okay, and measuring them continuously, you implement this POVM, which is great. All right. Fun fact, if I have a lot of friends who like to think about parafermions. So, you know, in the case of spin coherent states, my argument for, or one of the canonical arguments for why you might care about a spin coherent state POVM was in terms of copies. So here, my sort of reason why you might be interested had nothing to do with copies. So you might have wondered about copies. So it turns out that copies of BCS-coherent states carry a representation of the parafermion algebras, in case that means anything to you. Oh, right. Are there any questions about that? All right. So now I'm going to do my best in the sort of 5 minutes I have left to give you guys a sense of how you can comprehend the dimensions of this space of BCS coherent state outcomes. Okay. So let's see what we have here. So I guess not to forget, so I'm going to compare the BCS coherent states to spinning Glauber or traditional coherent states. So of course the manifold is uniquely defined. Well, I say of course. The manifold is uniquely defined by an associated Lie algebra. And when you think about the manifold directly, you should, or geometrically, you should appreciate that there's really two canonical things you would want from a manifold. So one of them is you want to know what it means to move around. So that's what these displacement operators are doing, telling you how to move around these spaces. But also, also very important are the kind of harmonics that can be carried by the manifold. Okay, so in the case of the plane, the harmonics are just plane waves. In the case of the sphere, harmonics are the so-called spherical harmonics, and this manifold of BCS coherent states also has a set of harmonics. All right, so when you quantize these manifolds, just to review again, these displacements and these harmonics appear in the quantization in terms of coherent states for points. So they're the quantum analog of a point in the manifold. And these irreducible tensors for play the role of harmonics in the Hilbert space. So in the case of BCS coherent states, the irreducible tensors are just polynomials in the Majoranas of fixed degree. So they transform into, all the quadratic things transform into each other when you conjugate them by Bogoliubov transformation. All the quartic stuff transforms into each other by Bogoliubov transformation, etc. Okay. And you can think of this in the same way that you think about polynomials in spin components transforming into each other, as you do for atomic systems. Great. And something that's important is this connection between irreducible tensors and harmonics is precisely what is at the heart of the so-called phase space correspondences, where, you know, traditionally we like to think about states, for example, as operators over a Hilbert space, but you could just as well formulate your theory in terms of functions over a phase space. Okay, which is useful here because, well, in terms of functions over the phase space, well, if we did this measurement on a state, we would get the Q function of the associated phase space correspondence. All right. So all that being said, just to summarize, so in terms of manifolds, manifolds don't care about whether you're applying them to classical theories or quantum theories. If you apply them to classical theories, then you're going to be interested in things like particles, which are points that evolve in time by an equation of this form. Or you might be interested in waves moving over the manifold. And I think of functions and waves as essentially being the same thing. So I decided to put a Wigner function here. Maybe that's not a good idea, but you could think of this as a way if you wanted to. And if you were to apply these manifolds to a quantum theory, then, well, points are replaced with things that have quantum fluctuations, and observables are in terms of polynomials and the generators of the manifold. All right. So what you should get out of this is there are two things to a manifold: points and harmonics. They can show up in the classical sense, they can show up in the quantum sense. But I like to think of the manifold as fundamental. All right. So then the purpose of the rest of these slides was to give you a sense of how points move around in the manifold and how you calculate harmonics. But because of time, I need to choose. So this one's important. I think you'll like this one. Okay, so what I have here, so I'm going to try to tell you how to make a coordinate system for the BCS manifold of BCS-coherent state. If you're familiar with optical systems, this is going to be the analog of the Bloch-Messier decomposition, which is why I wrote this here. So what we're going to do is we're going to consider a general unitary generated by a Hamiltonian quadratic in these fermion operators. So a nice fact is that every such operation can be decomposed into a number preserving operation, as I'm representing by this W, followed by a, I never know what to call this thing. I'm going to call it a Cooper oscillating, a unitary generated by a Cooper oscillating generator. Sometimes if you have an optics background, you'd want to call this a two-mode squeeze. But if you think about where the term squeeze comes from, that's just a really awkward term to apply to this. But I might end up calling it squeeze anyway, we'll see. But then further, unitary Hamiltonians that are of this form can be diagonalized by number preserving operations. And in this case, the sort of diagonal two-mode squeezers are commuting two-mode squeezers are the maximum number of commuting squeezers are always going to be two-mode. There's no such thing as a single mode squeezer for a fermionic system. Okay, so each of these can be diagonalized in terms of a set of commuting two-mode squeezes. And then this V is just what you get from this diagonalizing unitary being multiplied by this first one. Oh, right. Are there any questions here? So every Bogoliubov transformation can be written as a number preserving unitary, followed by a canonical set of commuting two-mode squeezers, followed by another number preserving unitary. I gestured this as if time went from right to left, but I mean for it to go from left to right, as demonstrated by putting a little vacuum here. So I'm thinking of this as now the input of this operation. And this kind of decomposition theorem, in fact, allows you to begin to coordinatize the manifold of BCS-coherent states. In the same way that, say, the Euler decomposition allows you to think about spherical coordinates. So let me explain what I mean by that. So this first number preserving operation does nothing to the vacuum. Well, you can think of these commuting two-mode squeezers as displacing you from the vacuum in very much the same way as a polar angle displaces you from the north pole of a sphere. And then given a second round of these number preserving operations, now that you've been displaced away from the point that has these as its symmetry, you end up getting swung around the manifold. Okay, so you can think of these as like polar angles and these as like azimuthal angles for the manifold D3. All right. Are there any questions there? So this is literally a sphere, but hopefully you can imagine that it abstracts according to the structure one enjoys with this kind of a decomposition. So in general, these kinds of decompositions are called KAK for lack of creativity. K just representing, in this case, the number preserving subgroup of all Bogoliubov transformations. Yeah. All right. So you may notice this looks like a singular value decomposition. And so you can calculate its parts in exactly the same way that you calculate a singular value, the parts of a singular value decomposition, except that the conjugation is not Hermitian conjugation. Rather, it's Hermitian conjugation followed by group conjugation by a special element. This element is very physically meaningful. It is, in fact, the fermion analog of a Fourier transform, which is defined by imparting an I on the complex amplitude. And yeah, all of this is just to sort of break down what it is that makes singular value decomposition so special. All right, so I'm just going to move on. I think here I'm just going to quickly summarize that just like you use only half a circle to define the polar angle on a sphere, because every latitude intersects the entire circle twice, so too, these number preserving operations swing you around the manifold of BCS-coherent states in such a way that there are actually multiple thetas that could give you the same omega. And so in this case, if I fixed 4 modes, then given a sort of theta 1, 2, theta 3, 4, if I swung it around the rest of the manifold with the second number preserving operation, it would actually intersect the set of all states orbited here 8 times instead of 2 times like in this sphere. And this triangle is called a Weyl chamber. This triangle is called a Weyl chamber. And these numbers are just the dimensions of the orbits that are moving through the rest of this 12-dimensional manifold. Oh, great. So then the other thing I said was important about manifolds was harmonics. If you think about spherical harmonics, if you've ever solved for them, my guess is that you solved for them in the following way. The first thing is you appreciated that you could express the Laplacian over a sphere like this. And then you would normally make an ansatz that these YLMs separate as a product of a function of phi and a function of theta. And then by some miracle, that ansatz works and you arrive at a formula for all the YLMs. So you might think you might want to do that in general. So I put a drama sad face here because, well, that's a lot of work. So we were just talking about 4 fermionic modes corresponding to a 12-dimensional manifold. So first of all, you'd have to do enough work to express this Laplacian in terms of all 12 of those dimensions. And then you could imagine doing a separation of variables, but I think that doesn't work. I haven't tried it myself, but there is a better way. And that better way has to do with a realization that Hermann Weyl and a student of his, Peter, had, which is that you should think about the matrix elements of representations of a Lie group as, well, it turns out that they are a complete basis for the space of all square integrable functions. And once you have square integrable functions, you have things that interact very nicely with things like Laplacians. And you can get your YLMs in a different way. Yeah, so there's something you have to supplement the Peter-Weyl theorem with to actually go from these matrix elements to these YLMs. And that's basically identifying representations that have vectors in them that have the right symmetry. So, right, because, you know, points in the manifold that you are representing had symmetry, like the vacuum had symmetry under number preserving operations. So you sort of have to know all of the lambdas, which is easy to do. And I'm asking you to trust me that that's right. And then for each lambda, you have to identify whether or not it even has states with symmetry and the right symmetry in it. Okay, so for the spherical case, that would be the same thing as appreciating that all representations of rotation can be decomposed into fundamental representations, irreducible representations, excuse me, that are denoted by integers or half integers, but also understanding that for spheres, that only the j's of integer value have states in them that are invariant under z rotation. Okay. All right, so this was going to be I'm going to pass this real quick and summarize it for you. This was just supposed to represent how, knowing just the Lie algebra alone, you can actually calculate the invariant measure over the entire group. Basically, it's just you multiply a bunch of sine functions, the sine functions being specified by the Lie algebra of the manifold. So that's great. You get these degeneracies in them that remind me of this symbol you see a lot in New Mexico, the sun. That's why that's there, in case you noticed it. All right. And from there, you can actually start calculating harmonics. So this is me calculating some harmonics. And for your viewing pleasure, here are 4 of my favorites. I really like this one because it has cusps in it. Look at that. All right. Okay. So, and with all of that technology, you can calculate to your heart's content. So something you might be interested in is the Wigner function of the vacuum state itself. Well, it looks like this. In the community, there has been a lot of talk about possible relationships between, in general, between quasi-probability positivity and classicality. And this is an explicit demonstration that if there is any relationship between the two, it's a little more subtle. Because it was originally conjectured that negativity would correspond to non-classicality, but I think a lot of people would agree that the fermion vacuum is very classical in the sense that there is so much about it that you can simulate just with a classical computer. Nevertheless, it still has negativity. I believe there is still a relationship between these two, but it's more subtle. In fact, it is this project through which I met Chris Ferry. Yeah. Okay, so just to summarize again, I talked to you guys a lot about spin coherent state POVM, stated with authority that it generalizes to any semi-simple Lie group, and then applied it to fermionic systems and tried to give you guys a sense of the phase space associated with the outcomes of the fermion coherent state POVM. All right, so as was said, I am coming to Sydney as soon as I can. Very much looking forward to working with you guys. In particular, lately I've been working with, well, not lately, like a month ago, I had last corresponded with Elijah on this project we've been working on over the last year. A very exciting project, but I will leave it as mysterious unless you guys have questions later. And if there's anything you take away from this talk, I hope it's the following: that there is a measurement for fermionic systems, which has as outcomes a phase space, which in fact people have been interested in for other reasons. And the way that you can do this POVM is by isotropically measuring these kinds of observables. Excuse me. And you can't find anything about fermions particularly in this paper, but you can find out about the generalization abstractly in this paper. And that the outcomes of this measurement are particular manifolds that can be understood. And well, I just really like manifolds. So with that, I'd like to thank you for your attention.
I'll clap on behalf of everyone. I don't know if you can
I think everyone can unmute.
I can hear the clapping all around Sydney.
God, and I'm way over time. I'm so sorry about that.
Oh no, that's all right. That's why we suggest a shorter time, because you're within the actual time.
Any questions?
Okay, so, yeah, any questions, right? As people figure out how to unmute themselves. I'll start. Chris, so when we think about the phase spaces for the conventional phase space that most of us are used to with a particle and on a line, or even the spin phase spaces, there kind of existed a classical phase space before it was considered in quantum mechanics. So is it fair to say that then when we think about fermions, that the space isn't classical because it doesn't really exist in the classical sense?
Yeah, that's an interesting question. So yeah, in my mind, I think about superconductivity, or okay, I think of the geometry associated with BCS-coherent states as in fact not quantum at all, right? And what that means is that, you know, at least as a set of points, yeah, you can calculate everything you want about them without using this exponentially large set of matrices. In fact, that's why you can diagonalize the BCS Hamiltonian, is because you can replace these exponentially large matrices with just quadratically large matrices. So in that sense, right, anything that has to do with quadratic fermionic systems is classical because, you know, you have an exponential speed up in the kind of calculations you would want to perform. Does that answer your question?
Yeah, I think so. I mean, I guess, I mean, the way that you phrase it, it still kind of presupposes a lot of quantum physics, right? You're saying you're kind of casting it as a restriction on the full generality of quantum physics. The question was more like, does there exist some classical notion out there independent of quantum physics for which this would be a natural phase space?
Oh, I see. Well, the group was SO2N, and the symmetry was isomorphic to a unitary subgroup of SO2N. And I think when Cartan discovered this space for himself, he had a very weird way of thinking about, so, you know, SO2N you can think of as rotations in a 2n dimensional space. But then thinking about what it means to have an object that has a UN symmetry, you have to get kind of creative. And so, like as you're pointing out, for fermionic representations, well, vacua have very naturally a symmetry which is isomorphic to UN. But no, I don't know any way of thinking about shapes in 2n dimensional space and rotating them in such a way that they have a UN symmetry. So I think that was just a really elaborate way of saying, no, I don't know of a classical example of this phase space.
Okay. Thanks.
So I think maybe I have a question if there's no other hands. So as an experimentalist, I didn't necessarily follow some of the mathematical details, but I can see that what you seem to have shown is that there's basically a similar structure underlying these BCS coherent states as, for example, that has many of the same properties that we can think of when we think about the coherent states that are incredibly useful, for example, in optical systems, yeah. or in microwave optical systems, quantum optics.
Yeah, I agree. Yeah, very exciting.
Present physical things in a lab, how we can take the vacuum state and create displacements on that, how we can use that to prepare non-classical states like cat states, and there are ways of creating even continuous variable resource theories and computational structures. Can you give a sense of how this might play out for this example of the fermionic systems and the BCS type systems? Is there a way that one can imagine building that sort of scaffold of
right.
more sophisticated ideas?
Yeah. So it turns out that 4 fermionic modes is sort of the simplest example you can consider where there is a non-Gaussian state. Okay, and that state has a special name. It's called the Bravais resource state, or at least in Monotony, I call it the Bravais resource state because Sergei Bravais wrote a paper talking about how you could inject the sort of four-mode fermionic non-Gaussian state into a topological quantum computer as a magic state. So, you know, you could do this kind of measurement on what you would presume. So, you know, you would hope to prepare Bravais resource state, and you can do this coherent state measurement on that state and take a look at its Wigner function in this phase space. And just like you sort of verify that you're preparing a cat state, you would be able to verify that you were preparing Bravais resource state. And I think that is the extent to which I imagine the next step of applying such a measurement. Does that answer your question?
Yep, I think so.
Cool.
Chris, I want to ask you a question, but I think I might know what the answer is. So I guess maybe it's more of a comment. So when we think about the words such as squeezing, my guess is that it's from this geometric picture about phase space, and I think a lot of intuition, at least in non-relativistic quantum physics, is developed from these phase space representations, especially for spin systems. Do you imagine that such a thing could happen for fermionic systems, where we start to think about phase space as much as we think about algebra?
So you're saying, can new perspectives emerge just from understanding this phase space better? Is that essentially the question? If that's the question, then the answer is yes, of course.
I figured as much, yeah.
Yeah, it's very exciting. You know, so something to point out for those who are making analogies with bosonic systems is to notice that, you know, these displacement operators are not linear in the amplitudes, right? They're quadratic. So it would be like, and it's true that in bosonic systems, you could consider using a different phase space, which was the sort of space generated by quadratic observables. But this is not really done for other reasons. And the reason I'm considering these sort of displacements via quadratic observables is because linear observables don't, well, there's two arguments. So one of them I don't understand and one of them I do. So one of them the one I don't understand is everybody tells me that a single fermion amplitude is not observable. And I don't know why that's true. Something super selection, something dimensions and relativity. But I'm not sure I buy it. But the second reason is if you think about the displacement operators associated with linear observables, you find that they don't close. So that's the same thing as saying that commutators between linear observables create quadratic observables. Well, in the bosonic case, right, commutators between linear observables make the identity. So in terms of analogies, that's quite the difference between bosonic systems and fermionic systems, and probably one of the reasons why people have not explored them very much farther. I just had to make that comment, excuse me.
Oh, there's a Adrian has asked a question in the chat. I guess since I'm got my mic unmuted, I'll just read it to you. Hi, Chris. Thanks for the great talk. I have a question about your scalable tomography scheme, but I can't speak right now because of the background where I am. My question is, suppose, do you want to guess? Let's play a game. No, I'm just kidding. My question is, suppose you have a qubit to fermion mapping, like the Jordan-Wigner transformation, and you characterize this Q omega function by your scheme. Can one back out the Pauli expectation values in the qubit picture from the Q function, and how would one do it?
Oh God, right. Okay, so, right, so you would have to, okay, So if you do this measurement on some state, then I'm going to take as assumption that you have the Q function, right? So it is the outcomes of measuring a state. So of course you want to translate that now into a prediction about expectation values, in which case what you'd have to do is calculate the P function of whatever spin observables you want. And that is going to be difficult if, you know, because the things you'd want to measure are like two local spin observables. But in terms of how that translates to irreducible tensors in the Majoranas, right? So if you were to do the Jordan-Wigner transformation and write a two local term, I believe you get a monster, and Adrian, you know this better than I do. I believe you get a monster of a polynomial in the Majoranas. And then because you get a monster of a polynomial, you also get a monster linear combination of special functions according to this phase space. But you can do it. I would have to be pretty strongly pressed to do it if I were to ever agree to. Yeah, so the calculation wouldn't be fun for two local observables, but you can do it. Does that answer your question, Adrian?
Depends on how fast. Oh, yeah, yes, yes, it does apparently.
Woo.
All right. Okay. I think it's a good time to end there. And thank you very much, Chris, for the talk.
Thank you.
And we hope to see you in Sydney soon.
All right. Until next time.
All right. Stay safe, everyone.
Great.
Bye.
Thanks.
I'm going to end the meeting for everyone.